Okay, this tutorial will be about plastic deformations and well, nonlinear geometry as well. I I will show you how to pull this shape here. We're gonna pull it upwards here and see when it breaks, if it breaks and when it breaks. And so what we're gonna do is we're gonna lock it down here, and then we're gonna take this edge and just pull it upwards. The length of this is 50 millimeters. We're gonna pull this 30 millimeters, and so it's a forced displacement, and we're going to see what forces are going, what resulting forces are going to be here up here, and also where the material starts breaking apart. Okay, so let's start with defining the material. So we're going to define a elastic elastplast material. So we'll go to mechanical, choose elastic. We're working with millimeters, so this is 210 to E3 here, 210,000 megapascals. Poisson's ratio is 0.3. And then we're going to define a plastic material. So go to plasticity, choose plastic. And now we have a list. So you can just right click here and choose read from file. And then I put mine in the temp folder. So that's the plastic model data.txt. So grab that and yeah, start reading values into table row 1, start reading values into table column 1, and press OK. So your data should look like this. So the yield stress is at 200 megapascals, and the plastic strain at that point must be 0. Okay, so everything is linear up until this point. This is the yield stress. So from there, this becomes nonlinear, and you can actually show this. So if you mark this, right click, create XY data, call this plastic data, and just press OK. I already have that, so yeah, overwrite, and then go to results. Yeah, we're gonna go into plastic data here, and just click plot, and this is what we get. So at 200 megapascals, we have 0% strain. And then as we move upward here, next point is you can actually probe these values. So the next point is up there. It's at 374, and that's 0.09436 strain. So yeah, 9% strain, and it goes up until 30% strain at around 500, or at 500. So what you could safely say that at 500 the thing is broken. Anything beyond 500 is just not going to be of any interest, because beyond 500, stresses beyond 500 are just not there. The thing is broken at 500. Okay, so cancel out of there and go back to the model, and let's expand the model here, and actually, oh yeah, double click cancel and press OK. So now we have a elastic plastic material here. Okay, so next define the section, create. It's a homogeneous. Continue the elastic plastic material, yes, and the thickness of this here is 10. So we're gonna put this to 10. Okay, and then we're gonna assign this to this shape. All right, and moving on, we have now the mesh. Actually, I'm gonna go ahead and save this. So now I've saved it. We're gonna create a step, or actually start with this assembly. Create the part. Okay, then we're gonna go ahead and create a step, general, continue, and yeah, so we're gonna use nonlinear, but yeah, let's go ahead and use nonlinear. Then incrementations, we can just increase this to 1000. Change the increment size to let's do this fine. Let's go with 0.01 initially, and then the maximum will be 0.05, and the minimum 0.8, 10 to the power of minus 8. Okay. Yes, so leave these as default. Actually, we're just gonna make sure that we have the reaction forces selected. Yes, that's right, because we're gonna need these. And also it should by default select the plastic strains. Let's check that it does. Yeah, PQ, that's what we need. Okay, so boundary conditions. So the first are going to be locked, so let's continue here and select this thing, the lower side there, and then completely clamp this at the lower side with the displacement rotation selected. Okay, and then go ahead and create another one. The displacement rotation, continue, choose this here, and yeah, click done, choose the Y direction, go positively 30 millimeters, and its amplitude, yeah, ramp, just increase it gradually. Okay, so the model is complete now. You can save it, create a job, continue, okay, and submit. Alright, so the job is done at 65 increments. We can dismiss this and we can go to results. Right click on results and just pan it in here. And let's see here. Oops, there we go. This thing has fallen apart. Alright, so let's change the contour options to blended just to make it a little bit nicer. Continuous, okay, and yeah, and let's see what happens if you press the animate time history. Oh yeah, oh yeah, and there we go. Okay, so what's happening at the very end here? This is very much broken. I mean, you know what? Let's go and change the viewport. Viewport annotation options, legend. Yeah, it is set to engineering. Great. Okay, and let's see the limits here are auto compute and okay, specify 500. There we go. Okay, so let's show the location. Yeah, so this is the maximum. This is where the crack will initialize. At this point, we have at this point it's already breaking off, so it's here. So the crack will initialize here, and it's gonna spread through this thing. So this is where the kink is going to be. So all this gray area here means that this is the break point. This is where the material is breaking apart. Okay, and what we can do now is switch to. You can take a look at the PEQ, which is the plastic strain. So there's no plastic strain yet anywhere. And actually, let's see here. Autocompete. Yeah, this needs to be set to auto. So time step 7, nothing. And then here we have a little bit plastic strain, and it's increasing. And there we go. Okay, so I can close this down, and let's take a look at some nice. Let's see that this is, yeah. Let's see that we're actually, this is a C beam, right? And we're pulling it apart. So there's actually another. This is mirrored right across this edge here, so we can visualize that. Let's do that. Go to View, and go to let's see here, ODB display options. Select that, and then go to mirror pattern. And so we need to create a coordinate system. So we're gonna choose this. We're gonna let the system follow a single node, because as we pull this apart, the coordinate system is going to change, and we still want this thing to be mirrored even if we pull it apart. So system following a single node, rectangle, continue. And then we're going to put the origin to be in this point. And yeah, there we go. You just click there and you have it. And then in the ODB display options, you can select this CSIS1, and then we're going to mirror it across the plane, across the XZ plane. So that would be this one. And press apply, zoom out a bit, and you see here what's happened. Okay, so now the complete solution is just mirrored around this plane. Now, once we have this, we can display stuff with it, so we can see here what's happening. As if this was a complete thing, it's gonna break apart at this point here. Why at that point? Because we have a stress concentration right above this this notch here. All right, so what else? Well, let's pause this, go back, and take a look at the residual forces, or the reaction forces, sorry. So when we take the RF, you can see here that at this point we will get forces. So we want to know what the sum of these forces are, right? So let's go ahead and create some XY data. ODB field output, continue. Unique nodal, go down to reaction forces, and we want to do it in the Y direction, so that's RF2. Go to element nodes, edit, zoom in, and select these. And yeah, select these and go to highlight in the viewport right there and save. And the XY data will be extracted from a field output using field names. So okay, and there you have it. In the result pane, you can see the result points there. So now what we're going to do is go back to XY data and do operate on XY data and continue, and you get this box. So what we're going to do now is choose these points here, right? And take some. Okay, so we're gonna grab some, grab all of these points, add to expression, and well, let's create XY data. Save this as the total force, total reaction force. Okay, cancel, and then we have this force. We can plot it. So this is what we get. So you have this elastic part here. So you have force, and then you have displacement down here. And this is scaled from 0 to 1 now, right? So the displacement goes from 0 to 30, but yeah, it's scaled. The interesting part here is that if we zoom in a little bit, If you zoom in here, you can see that there's a linear part and then it becomes nonlinear. And it goes up to this point and then it goes down beyond that. So this is the true stress curve, or the natural stress curve, sorry. So we can take this and we can actually see here what the maximum force is, which is 47,000 newtons. So at 47,000 newtons, the whole thing breaks. So that's a nice analysis tool. Okay, now we know how to create a plastic model, pull it apart, and see what's happening. Got it? Good.